Half a watt. That's how much electricity is being spent right now, roughly 16 billion miles from where you're sitting, to keep one small motor turning inside a machine most people assume died years ago. That motor doesn't collect anything. It doesn't send anything home. Its only job is to rotate a sensor slowly in a circle, and the instrument that sensor belongs to was shut down back in April. So it's turning a switched-off instrument in the dark in a place no human-built object has ever been. The engineers at NASA's Jet Propulsion Laboratory left it running on purpose. They left it running because there's a plan being attempted this summer, and if that plan works, they might be able to wake that instrument back up. They didn't want to close the door all the way. So they spent half a watt they can barely afford to keep a hand on the handle. I want to walk you through what's actually happening with Voyager 1, because the version you've been seeing in headlines is not quite the version the engineering team is living. If you like your space news with the numbers intact and the drama left where it belongs, subscribe. That's what this channel does. Now, let me take you back to the 27th of February. It was supposed to be an ordinary day. Voyager 1 performs a maneuver every so often called a roll. The spacecraft turns itself slowly, deliberately, so that its magnetometer can be calibrated. Think of it as the machine stretching to check its own instruments. The team has done this for decades. There's nothing exotic about it, except that during that roll, the power levels aboard Voyager 1 dropped, not on schedule. Not by the amount the models predicted, they dropped unexpectedly. To understand why that sentence made a room full of extremely calm engineers sit up straight, you have to understand what Voyager 1 is running on. There are no solar panels out there. Sunlight that far away is useless. Voyager 1 carries a radioisotope thermoelectric generator, which is a device that takes the heat from decaying plutonium and converts a portion of it into electricity. It's beautifully simple and completely unforgiving. Plutonium decays on a schedule that no engineer can argue with. Every single year, both Voyager spacecraft lose about 4 watts of available power. Every year, without exception, without appeal. Reporting on the mission this year has put Voyager 1's usable power at somewhere in the low 20s of watts. Sit with that number for a moment, because it's the whole story. 20-something watts. Less than the little bulb over your kitchen sink, less than the light inside your refrigerator when you open the door. That is the entire electrical budget for a spacecraft the size of a small car that is currently the most distant object humanity has ever built. And here's the part that makes the February dip genuinely dangerous. Voyager 1 has an automatic safety system on board called undervoltage fault protection. If the available power falls below a certain line, the spacecraft doesn't wait for permission. It starts shutting things down by itself to protect its own survival. That sounds like a good thing. In principle, it is. Kareem Badarudin, the Voyager mission manager at the Jet Propulsion Laboratory, has compared it to the safety net stretched under a trapeze artist. You're glad the net is there. You never, ever want to be the reason it gets used. Because if fault protection triggers, several things happen at once, and none of them are good. Science data stops flowing home. Components get powered down by a computer that's making decisions based on 1970s logic. And then the team on the ground has to climb back up and recover everything by hand from 23 hours away with no guarantee that every instrument it turned off will agree to turn back on. So the engineers made a choice. If the spacecraft was going to lose something, they'd rather decide what than let a 49-year-old fault protection routine decide for them. And this is the detail that tells you what kind of people run this mission. They didn't have to invent a plan in the moment. Years ago, the Voyager science team and the Voyager engineering team sat down together and wrote a list. An order. If we have to start turning things off, this goes first, then this, then this. They did it while everything was still working, while nobody was panicking, while they could still think clearly about which measurements mattered most. Each spacecraft launched with 10 instrument packages. 7 have already been shut off over the decades. When the power dipped in February, the team pulled out that list and looked at what was next. Next was an instrument called the Low Energy Charged Particles Experiment. On the 17th of April, They sent the command. I want to be precise about what that command actually involved, because it's a strange kind of surgery. The instruction left Earth and traveled for roughly 23 hours before it arrived. Then the shutdown sequence itself took a little more than 3 hours to complete, and then the confirmation had to travel 23 hours back, which means the team pushed send and then waited almost 2 full days to find out whether they'd done it correctly. You need to hold on to that, because everything else in this story runs on the same clock. Nobody at the Jet Propulsion Laboratory is flipping a switch. There is no repair crew, there is no diagnostic cable. Every single thing they do to that spacecraft is a letter. They write it, they send it, it takes a day to arrive, and the reply takes another day to come home. They are maintaining the most advanced machine of the 1970s entirely by correspondence, and the postage is measured in hours of the Earth turning. Now, about the instrument they had to silence. The low-energy charged particles experiment had been running almost continuously since 1977, almost 49 years. It measured ions, electrons, and cosmic rays, particles coming from our own sun and particles coming from the wider galaxy. And it did something no other instrument in history has done. It felt the boundary. When Voyager 1 crossed out of the sun's bubble and into interstellar space, that instrument was one of the ways we knew. It sensed the change in the particles around it. It's the reason we can say with confidence that there is an edge to our sun's influence and that something built by human hands has passed through it. It has also mapped out pressure fronts and regions of different particle density in the space beyond, places where the interstellar medium is thicker or thinner, which is information we have no other way of getting. There is no telescope on Earth that can measure the particle density of the space between stars. You have to be there. Only 2 objects are there, and one of them just went quieter. Matt Hill, who leads that instrument at the Johns Hopkins Applied Physics Laboratory, put it plainly in comments to reporters. He's hopeful the engineers can find the power to switch it on again. He also noted, with the honesty you find surprisingly often in this community, that the team has a long record of pulling off miracles with the power supply, and that eventually the streak has to end. And now we come back to that half-watt motor. The instrument has a rotating platform. A small stepper motor turns the sensor so it can scan in every direction rather than staring at one fixed patch of sky. When they built it here on Earth, they tested that motor to about 250,000 steps. That was considered generous. It only had to survive the flybys of Jupiter and Saturn, a mission of about 4 years. Nobody was designing for a career. That motor has now taken more than 8.5 million steps. 8.5 million. Against a design test of 250,000. That's like buying a car with a warranty good for 100,000 miles and driving it 3.5 million. And it gets better. To save power, the team had already turned off the supplemental heater that kept that part of the instrument warm. The temperature there fell to about minus 62 degrees Celsius. That's colder than the coldest natural temperature ever recorded on the surface of Antarctica. Steel gets brittle at temperatures like that. Lubricants stop behaving like lubricants. The motor kept stepping. Stamatios Kremigis, the principal investigator for the instrument, called that result the stuff that dreams are made of. He's been with that instrument since before it launched. Nearly half a century of watching one small motor refuse to quit. That's why they left it on. Half a watt out of roughly 20, spent on a motor attached to an instrument that isn't currently doing anything, because the people who know that hardware best believe it may still have something left to give. If that detail landed for you the way it landed for me, drop a comment. I'd like to know which part of this story you hadn't heard before, because now we get to the reason all of this is happening right now in this specific month rather than next year. The team has a plan. Internally, they call it the Big Bang. Here's the concept. On both Voyager spacecraft, there are powered devices that were designed in an era when power wasn't the constraint. Heaters, systems, components that draw more current than a modern equivalent would. Over the years, engineers have been turning things off one at a time, carefully, conservatively, watching for a reaction after every move. The Big Bang is the opposite of that approach. Instead of turning off one thing and waiting, the team intends to swap out a whole group of powered devices at once, turn several things off, turn lower power alternatives on, all in one coordinated sequence, hence the nickname. The goal isn't just to save watts for the sake of saving watts. The goal is to keep the spacecraft warm enough to keep doing science. And that word, warm, is where the risk lives. Interstellar space is not a mild environment. Voyager's hydrazine fuel lines have to stay above a certain temperature or the fuel inside them will freeze. If those lines freeze, the thrusters can't fire. If the thrusters can't fire, the spacecraft can't correct its orientation. And if it can't correct its orientation, that 12-foot dish antenna drifts off Earth. The moment that antenna stops pointing at us, the mission is over, not damaged. Over. There's no recovery from a spacecraft that can't hear you and can't answer you. So every watt the engineers claw back from a heater is a watt they've taken from the thing keeping the fuel liquid. Every watt they leave in place is a watt they can't give to an instrument. That's the trap. Save too little and the power runs out. Save too much and the spacecraft freezes to death while fully powered. There's no third option and there's no margin left to be sloppy with. That's why the sequence matters. The team decided to run the Big Bang on Voyager 2 first. Voyager 2 has slightly more power in reserve and it's roughly 2 billion miles closer to Earth, which shortens the letter writing time and gives the team a faster read on what went wrong if something goes wrong. The tests were scheduled for May and June of this year. And if those tests went well, the plan was to attempt the same procedure on Voyager 1 no sooner than July. We're in July. Now let me be very clear with you about what I know and what I don't, because this is exactly the point in a story like this where a lot of channels start making things up. As of this recording, NASA has not published a public result from the Voyager 2 tests. There's no press release announcing success. There's no announcement of failure either. That is completely normal for this mission. The Voyager team publishes when something is confirmed, not when something is in progress. And a procedure like this generates weeks of telemetry review before anyone says a word about it. Silence from the Jet Propulsion Laboratory is not evidence of a disaster. It's just how careful engineering sounds from the outside. So if you see a video claiming Voyager 1 has been saved, or a video claiming Voyager 1 has been lost, in July of 2026, that person is guessing. I'm not going to guess with you. I'm going to tell you what's scheduled, what's at risk, and what the actual signal will be when it comes. While I'm being blunt, let me kill two other stories that circulate constantly about this spacecraft. The first is the claim that Voyager 1 detected something out there that NASA is hiding. It didn't. The measurements coming back are plasma wave data and magnetic field data, and they're published, and scientists argue about them in the open literature, the way scientists always do. There's no suppressed transmission. The spacecraft returns data at about 160 bits per second. That's slower than the dial-up modems some of you remember screeching in the 1990s. It is physically incapable of sending home a secret worth hiding. The second is the claim that the Voyagers were shut down or abandoned, or that the mission was quietly canceled. Also false. Instruments have been switched off, one by one, according to a list written years in advance for the explicit purpose of keeping the mission alive longer. That's not abandonment, that's triage. There's a difference, and the difference is the entire character of this team. The honest version of this story is dramatic enough. A spacecraft older than most of the people working on it is running out of electricity, and a small group of engineers is trying to buy it another few years using nothing but radio commands and a very deep understanding of hardware that hasn't been manufactured in 4 decades. And here's what makes the attempt credible instead of hopeful. They've done something like this before, and it worked. Go back to 2024 and 2025. Voyager 1 has multiple sets of thrusters. One set, the roll thrusters, used for pointing, had been considered inoperable since 2004. Dead. Written off. 21 years in the freezing dark with a heater problem nobody expected to solve. Meanwhile, the set that was actually in use had a different problem. Residue was slowly building up inside the fuel tubes, narrowing them, and the team could see the day coming when those thrusters would stop working too. Then, a scheduling problem turned into a crisis. The enormous 70-meter antenna in Canberra, Australia, the one dish powerful enough to send commands out to the Voyagers, was going offline for a long upgrade beginning in May of 2025 and running into February of this year, which meant that if the working thrusters failed during that window, there'd be no way to send the commands to fix it. So the team went back to the thrusters everyone had given up on. One engineer had a theory that a disturbance in a circuit had effectively flipped a switch and that the right command might flip it back. The problem was the risk. To test the dead thrusters, they had to bring them out of hibernation. If the heaters weren't actually working, and if the spacecraft's star tracker drifted too far off its guide star during the attempt, an automatic routine would fire those thrusters. Firing a thruster whose lines aren't properly warmed can produce a small explosion on a spacecraft that cannot be repaired, in a place nobody can reach. They sent the command on the 20th of March, 2025. Then they waited the better part of 2 days. The data came back showing the thruster heaters warming up. Thrusters that had been declared dead in 2004 in a machine drifting through interstellar space came back to life because somebody refused to accept that the file was closed. That's the team attempting the Big Bang. That's their track record, and it's the reason the phrase risky fix in the title isn't marketing language. Every one of these procedures is a genuine gamble made by people who've calculated the odds more carefully than you or I would ever calculate anything. So what's actually at stake if this works, and what's lost if it doesn't? Voyager 1 currently has 2 operating science instruments. One listens to plasma waves in the interstellar medium, essentially. It hears the density of the space between stars. The other measures magnetic fields. Voyager 2 has been running with 3, with its cosmic ray subsystem scheduled to be switched off sometime this year. If the Big Bang succeeds, the Jet Propulsion Laboratory has suggested at least one science instrument on each spacecraft could keep returning data into the 2030s. And on Voyager 1 specifically, there's a chance, not a promise, a chance that the low-energy charged particles experiment gets switched back on. That half-watt motor would stop being a bookmark and start being an instrument again. If it doesn't succeed, the margins tighten. The team goes back to the list, more things get turned off. And at some point, the science ends and only engineering telemetry comes home, which by NASA's own projections could continue until somewhere around 2036. A spacecraft still reporting its own vital signs, with nothing left to measure but itself. Understand what disappears at that moment. Not a satellite, not a redundant observation. The only 2 objects humanity has ever placed beyond the sun's bubble. Every model we have of what interstellar space actually is, physically, was built or corrected using data from these 2 machines. When they go quiet, that measurement stops and it does not resume because there's nothing else out there and nothing scheduled to get out there for a very long time. And the machine they're trying to save is, by any modern standard, absurd. Voyager 1 carries 3 computers with roughly 68 kilobytes of memory between them. Their processors run at about 250 kilohertz. The phone in your pocket has more computing power than every Voyager system combined, by a factor so large the comparison stops being useful. The spacecraft weighed about 1,797 pounds when it left Cape Canaveral in September of 1977. The engineering documents have been aging in filing cabinets for longer than most of the current team has been alive. It's traveling at roughly 38,000 miles per hour. It has never been repaired by a human hand and never will be, and it still answers when we call. Which brings us to November. On the 18th of November, 2026, at 16 minutes and 7 seconds past 2 in the morning Pacific time, Voyager 1 will be 16,094,799,000 and 96 miles from Earth. NASA has calculated it to the second. That distance is exactly how far light travels in 24 hours, which means that at that moment, Voyager 1 becomes the first object built by human beings to sit one full light day from home. A command sent at that instant takes an entire day to arrive. The reply takes another. Say good morning to Voyager on a Monday and you hear back on Wednesday. I'd caution you against reading that milestone as a triumph of speed. It isn't, really. In 49 years of continuous flight, Voyager 1 has covered a tiny fraction of 1% of the distance to the nearest star. What that number actually measures is patience. It measures a machine that survived launch, Jupiter's radiation, Saturn, decades of cold, fading heaters, clogged fuel lines, a computer that started speaking gibberish and had to be talked back into sense, and a power supply shrinking 4 watts a year, all while a rotating cast of engineers on Earth kept finding one more workaround. And it's still carrying the golden record, that copper disc with the greetings and the whale song and the photographs, bolted to the side of a machine now costing us less electricity than a nightlight. It will still be out there long after every one of us is gone, drifting toward the constellation Ophiuchus, passing within a couple of light years of a faint red dwarf star in about 40,000 years. But none of that is what the engineers are thinking about this month. They're thinking about watts, they're thinking about whether the fuel lines stay warm, they're thinking about a sequence of commands that will take a day to arrive and a day to answer, and about whether the machine on the other end of that letter will still be talking when the reply comes. So here's what to watch for, and I'd write these down. The first signal is any statement from the Jet Propulsion Laboratory about the Voyager 2 Big Bang tests from May and June. That result determines everything. If Voyager 2 came through it clean, Voyager 1 is next. The second signal is the Voyager 1 attempt itself, which was scheduled for no sooner than this month. Watch for confirmation that it was executed and, more importantly, that the spacecraft's power margin improved afterward. The third signal is the one I'm personally waiting for. If you ever see a NASA announcement that the low-energy charged particles experiment on Voyager 1 has been switched back on, that means everything worked. It means a half-watt motor that has taken 8.5 million steps at 62 degrees below zero gets to matter again. It means a 49-year-old instrument came back from the dead for the second time in this mission's history. And the fourth is November the 18th at 2:16 in the morning Pacific time. The question isn't whether Voyager 1 reaches that distance. Physics has already settled that. The question is whether, when it gets there, anyone is still on the other end of the line to hear it say so. Subscribe and turn on notifications. When the Jet Propulsion Laboratory reports what happened out there, I'll break down exactly what the telemetry says and you'll already understand what you're looking at.